So I have with me a special show. I have with me Bill Kramer of NCSA and the Blue Waters Project, and John Zebarth, also of Blue Waters and the Krill Institute. It's actually a different setup. We're actually in the same room for once. So if you guys could please introduce yourselves and give a little bit of background.
I'm John Zebarth with the Krill Institute, and I help the Blue Waters Project, especially with respect to the Great Lakes Consortium for Petascale Computing, which are the 28 universities and other educational institutions that came together to support the proposal that went to the National Science Foundation for the Blue Waters system.
I'm Bill Kramer. I'm the Deputy Project Director for Blue Waters, which means that I take care of the day-to-day issues of the project. We're right now in the deployment phase of crafting the system and getting it delivered and deployed, and going through additional activities to do software development for it and some value-added activities. And then we'll go into a 5-year period where we operate the system for science and engineering applications at scale.
Okay, so can you get a quick summary of exactly what Blue Waters is? What is its goals?
So Blue Waters is used in two terms. One is a computer system that is the leading system of its generation for open science. It'll be the largest system and the first sustained performance above a petaflop for a wide range of applications, all the science applications. The other part of Blue Waters is a large project that not only is about taking the system and putting it in place, but all the ecosystem, if you will, the infrastructure that goes around that system, including all the support that goes around that system. And one of the main focuses that makes this project a little bit different is we're doing a lot of very early work, even before the technology is available, to help applications prepare for running at scales that Blue Waters will be able to run at and doing transformative science problems. So we're actually engaged with 18 science teams right now that will increase over the next year or two. But we're working with them on their single CPU performance. We're working with them on how their code scale, re-engineering things, working on I/O bottlenecks, other types of bottlenecks, and also improved methodologies in terms of the programming environment, the tools that they use to work to understand their applications, modeling of their applications in a more formal manner, and a variety of other support activities, so that when the machine comes into existence at full scale, all these science teams are able to start running their real science rather than spending 6 months or a year tweaking and tuning and trying to figure out what to do. So we're actually doing that upfront work now via simulation and modeling and other things, and eventually access to hardware in order to get helping the science teams get ready for such a novel system.
So actually we had a question off of Twitter that requested, how many people do you actually expect will be able to take advantage? Will it just be these 16 teams that will be able to actually take advantage of a petaflop type system at day one? And then how many do you expect at 6 months, 12 months? What's kind of the ramp up in resources available?
So we think that there are many areas of science that can use the capability of a sustained petaflop, and to us that means really time to solution. So while you have to measure this some way that people can understand, it really is taking the applications that people need to use, or applications of the future a couple years in advance, science or challenging problems, putting them together, and then wanting to solve that problem in a certain amount of time. And there's two ways to look at this. One is who can use the entire system at a rate that translates into a sustained petaflop, and that's actually some of the benchmarks. The other thing is the what I call the sustained system performance. So if you think about a range of applications and their performance on their problem in their application, regardless of does it use the whole system or a quarter of the system or a tenth of the system, and you look at across all those things that are going to be running simultaneously, the system still will perform with all the petaflop across that. And that's the other way that we measure this. So it's not just a couple big things. It's taking a system that is targeted to be probably the most productive system coming out of the DARPA program, the HPCS program, the most productive system for people to use, and helping them make very effective use of that, regardless of the scale of the system. Now, we expect that in initial operation, there will be about 30 to 40 science teams that are allocated the vast majority of the time on the system. Those teams will almost certainly have multiple parties on it, but they're all trying to solve one science problem in a way that hasn't been done before. They may use multiple codes. As a matter of fact, most of them right now are double. We know at the moment there's been about 18 teams identified. There's going to be another call for proposals out that'll double that number. And then we have some other teams as well. The GLCPC has an allocation process in addition to this for some additional teams, but in general, the criteria is that people are proposing to do something at a scale well above what they can get in their normal resource allocations, be that on track twos or be that at the university computing areas. So we expect that there's a large number of science problems that need this type of resource. And the other thing is it's a very balanced resource, so it's not just raw flops, but it's memory bandwidth, it's low latency communication, all of which are unique features of this machine.
So what is actually the allocation process? You said there was a call for participation. The Great Lakes region has its own access for this. What exactly are you looking for when someone submits a proposal for time on Blue Waters?
So the Blue Waters project in NCSA is not the arbiter of who gets on the system. The vast majority of the time, at least 80% of the time, will be allocated through a new process that the National Science Foundation has set up called the PRAC process, Petascale Resource Allocation, or Petascale Computing Resource Allocation. The letters, they got switched to have a sayable acronym. That process will allocate 80% of the time, and that's where we're expecting this 30 to 40 teams to come from. There are a few other allocations for smaller percents. One is the Great Lakes Consortium that John can speak about. We have another one for education, general education, and probably some adjustment in a small amount of discretionary time that we could do for startup projects. So there are multiple ways to start, but the large allocations are going to come from the National Science Foundation. Do you want to add to that?
Yeah, the GLCPC Charter members, of which University of Michigan is one, they have an allocation, and there will be a process so that teams of scientists at those universities can submit problems to go on to this system, and hopefully then scale those up so that they fit under the PRAC allocation process in the future. So they're in a sense they're startup accounts, but they're really startup accounts of real science that has the potential of scaling.
So what can like I'm a sysadmin at the University of Michigan who's a member of this consortium, as well as highly involved in NSF, being a local resource provider, but I don't care if people use my local resource. I just want to enable science at my institution. What can I do as an admin to enable people to access either a Blue Waters resource or some other resource?
So I think they're probably looking to help people work to scale their problems to some degree, right? So having such a large resource, the goal is that it's used for things that can't be done in local environments, whatever. So I think helping people get to a point where they have the experience that they can say, okay, I have a method to get to the next level of science using computational techniques is an important thing. I think having well understood